Welcome to my session. So myself, Dr. Kode Jaya Prakash, working as Senior Assistant Professor in Department of Mechanical Engineering at VNR VJEC. So now in this session, we are going to discuss about this other remaining additive manufacturing processes like selective laser sintering, binder jetting, lens, that is the lens stands for laser engineered net shaping, and EBM stands for electron beam additive manufacturing, and Polyjet. So in this selective laser sintering and binder jetting, lens and EBM comes under powder based AM process, and whereas this Polyjet comes under liquid based. And coming to the case of next technique, selective laser sintering. So this selective laser sintering comes under powder based additive manufacturing, powder based. So here also no additional supports are required because the powder which is left over after entering is going to act as a supports, so that only this process and the previous process, the support structures are not required. And you can see this selective laser sintering is going to be developed by University of Texas in Austin and commercialized by DTM at Austin at 1987. The first SLS is going to be shipped in 1992. And you can see that here SLS is going to be a powder based form, and CO2 laser is going to be used for the final product. And CAD and STL file generation is going to be done and going to be is going to act as the input for this machine. And you can see here, as you can see this figure, the CO2 you can see here, this is a build platform, and this is a powder feed platform, and this excess powder take up. So here the roller, there's a powder leveling roller is going to be supply evenly the entire powder on the build platform evenly. And as soon as the CO2 laser is going to strike the initial layer of the surface of the platform, it is going to sinter the powder, and then after sintering is going to be done, and again the roller is going to be supply the powder even the build, that is a powder supply piston is going to move upwards, and the build platform is going to move downwards after curing of the every layer here. And then the leveling roll is going to be supply evenly on the build surface, and again second layer of the CO2 laser is going to be cured. Like that, series of layers is going to be built in this sort of sequence operation. What are the materials that are going to be used? So plastic powders and metal powders like ceramic powders and glass powders. These are materials. And coming to the case of more about SLS, this is additional information patented in 1989, and and advantage over SLS is variety of materials and ability of approximate common engineering plastic materials, and process simple, and powdery or porous surface is going to be done, and uncured metal is going to be easily removed, and again it can able to remove very easily by the blowing off. And coming to the case of the most important process parameters for the SLA, so part belt temperature, layer thickness, laser power is very important. So because it depends upon the type of metal which are going to use, and scan speed and energy density and powder shape as granules. And selective laser sintering applications, so that is so there's a aerospace. So for aerospace applications, and medical and healthcare, and electronics and homeland security, and military hardware, and in the case of rapid prototyping for engineering applications, functional proof of concept prototypes, design evaluation models, and these functional parts can be used widely with SLS process, and wind tunnel test models and product performance and testing. So these are wide variety of applications for SLS process. And you can see the current manufacturing system is the 3D systems. We can see the complexity of the parts. So this is how the complexity of parts is going to be built by using this wonderful SLS process. And coming to the case of key applications, and maximum build size is going to be done by 700 by 380 by 560 mm, and the resolution is Z 0.005 inches. And available materials is powder plastics, there's a of nylon, and steel, titanium, and tungsten, and other fiber reinforced polymer composites. And applications, structural components, functional models, and working prototypes, polycarbonate patterns, and for rapid tooling is going to be widely used. And advantages, so I told you there's no need of additional support materials because the powder which is not going to be cured by CO2 laser, the additional powder acts as a support structures. And and also coming to the case of drawbacks, it is expensive when compared with FDM process and other process. As you can see, this is the video of SLS process. So this is the entire setup of the SLS process. This SLS process, the CO2 laser is going to be cured here, the powder. So as soon as the sintering is going to be done, this optical scanning system where this the CO2 laser is going to be focused on the surface of the print bed, and this also comes under powder bed fusion, PBF, powder bed fusion. So how these layers are going to be built. See, this optical scanning system is going to guide the laser to initially to strike on the workpiece surface, and then the recoater mechanism is going to be supply evenly the powder on the previous layer which is going to be cured. So after each and every curing, it is going to be supplied by the recoater blade. The powder is going to be supplied. So you can see this how this laser is going to scan and cure the powder. And the adjacent powder itself acts as the supports. So as soon as the different layers are going to be completed, the elevator platform, the print chamber is going to move downwards. You can see here, it's going to move downwards. Sorry for the interruption. It's going to be moved downwards. And then the part is going to be taken outside, and the powder which is going to be sticked is going to be blown off and can be removed in the form of by the brush. So this is how this is going to be cured, and then see this enclosed chamber. So this is going to be taken, and then the powder is going to be separated and going to be cured with the help of a brush and sort of air. You can see the complexity of the parts. So this sort of racing industry, and also by complex models, this sort of models is going to be built. Okay, this is the working of SLS process. And coming to the case of three-dimensional printing or by binder jetting, the other name for three-dimensional printing is binder jetting. So this also seems to be like a SLS process, but only the thing is that CO2 laser is going to be replaced by the inkjet head. This inkjet head is going to dispense the liquid binder. So what are the different types of binders is going to be done for the binders is that phenolic binder, furon binder, and aqueous based binders. So depends on the application of whether it is casting or whether it is making of the molds or dies or making of patterns. So depends upon that we need to select the binders. Only the difference of SLS and three-dimensional printing is that the laser is going to be replaced by the inkjet head. The inkjet head is going to have the series of nozzles. So this series of nozzles, from this the binder is going to be jetted from the series of nozzles, and it ensures that each and every powder particles is going to be binded and firmly. As you can see that in this figure, the powder supply piston is going to move upwards, and then the roller is going to be supplied evenly on the build platform, and the liquid binder is going to be jetted on the surface of the workpiece, and it ensures that each and every particle is going to be binded. And as soon as the first layer is going to be dispensed, the fabrication piston is going to move downwards, and second layer of this roller is going to spread evenly the powder on the build surface, and again the binder is going to be jet on the previous layer. So like this, all the layers are going to be done, and then the part is going to be taken outside, and then it is going to be shown. You can see here. So how this is going to be done. The key applications widely used for multiple colors of printing is possible, and molds for sand casting of metals. And also advantage, it can generate complex components with internal degrees of freedom and economically versatile, and only the technology with full color output is available. Coming to the case of drawbacks, low resolution and limitation of surface finish. So you can see the maximum build size 14 inch by 10 inch by 8 inch, And resolution is low when you compare with other process, 640 dpi, and cost is also low, and starch powder and plaster powder and ceramic powder is going to be used. And you can see this video of this binder jetting for sand casting applications, as you can see here. So this powder is going to be supplied evenly on the build platform. The powder is going to be supplied. Yeah, this is how the powder is going to be evenly laid on the build surface. You can see the powder particles. It ensures that layer by layer a spread of the powder is going to be done. And that binder is going to be happen from the series of nozzles, liquid binder. As you can see, this is called as a inkjet head. This inkjet head is going to dispense the binder. You can see that liquid binder. So this binder is going to ensure that each and every single grain is going to be adhesive. So maximum precision is going to be taken. It ensures that each and every grains is going to be, and job box is lowered, and again the second layer of the binder is going to be dispensed on the previous layer, and similarly this a recoating mechanism is going to be supplied evenly on the build platform. Like this, each and every layer is going to be coated and then binded, and then the loose powder is going to be taken outside. And these also support structures are not required. So the powder which is adjacent to the, which is not going to be cured by the binder itself, acts as a supports. You can see the complexity of the part. So high growth industries applications, and for casting industry, sand printing, metal printing, and ceramic printing. So this is the working of this binder jetting. And laser engineered net shaping. This is purely for metal additive manufacturing. So this is comes under a DED process, it has a direct energy deposition. So here this elevator platform, this called as elevator XY table, is going to be moved along with the nozzle. So this nozzle is going to supply this powder and also this gas, this argon gas. This entire is going to be done in the argon chamber. It's going to be done in the argon chamber. So this closed argon chamber, this is a gas and powder is going to be supplied, and as well as this rotary table is going to move as per the nozzles, as well the direction of the nozzle which is going to be moved, is going to be used. So directly the metal is going to be deposited with the help of a one side of the nozzle, and other side of the shroud gas. So with the help of the supply of the gas, this powder, and the center option is going to have the laser. So these three mechanisms is going to take place to cure the powder, and directly the powder is going to be deposited on the surface of the build platform, as you can see here. And what are the materials are going to be used also, we are going to see now. These are the working of the lens powder. So this is the rotary build platform, and yttrium NdYAG lasers are going to be used here. Niobium, yttrium, aluminum garnet lasers, high power laser beam. So this powder is going to be supplied here. So this I'm going to pause for regarding materials. So titanium alloys, nickel based alloys, and cobalt alloys, and tool steels and SS, aluminum. So these are the different sort of materials are going to be used for this lens. You can see here working process. Powders are available in the multiple vendors, and because powders are very costly, so we need to select the proper application, and then we need to choose that powder which is going to be used here. You can see how it is going to be deposited. Powder and the gas, and in between a laser spot. And the specialty of this laser engineered net shaping is that it can able to add the parts. So add the portion of the parts wherever the parts are subjected to worn. If the parts are going to be worn, we can able to add the layers. Whereas with the other techniques, it is not at all possible. So we can able to add the parts which are worn. So this is a exclusive specialty of that of this lens. You can able to repair, and also we can able to fabricate the parts. Repairing of the parts, we can have fabrication of the parts. Both can be able to be done at a time. So this is how the lens building of thin wall intermetallic structure is going to be done. So directly the energy is going to be deposited and going to be fabricated. SS material is going to be used here. Okay, so is the lens repairing. So the adding of the material for the one parts. So with improved mechanical properties, the parts are going to be built with utmost improved mechanical properties. So this is about this working of lens process. And coming to the case of electron beam melting, this electron beam melting is also going to be done in the closed chamber. The closed chamber here, this closed chamber is going to fill with vacuum, because the electron bombardment is going to happen in the vacuum. As you can see here, this series of lens is going to be focused this electron beam. The tungsten filament is going to emit the electrons. So here you can see the two hoppers are going to be supply the powder evenly on the surface of the build platform. As soon as the first layer is going to be cured by the electron gun, the elevator platform is going to move downwards, and again on the previous layer, the powder is going to be supplied by one hopper, and then it is going to be spread evenly on the build surface, and second layer of the electron beam is going to be cured. So in this pattern, series of all layers is going to be cured by the electron beam. So this electron beam melting is widely used for the making of the for medical applications, mostly for orthopedic implants, for dental implants, mostly sort of medical application of tools. All the accuracy of the tools wherever it is required, it is going to be used with the electron beam additive manufacturing. As you can see, this Acram machine. Acram is going to be a manufacturer of this EBM. And maximum build size you can see 200 by 200 by 350, and speed is medium, and the cost is high. And because these available materials is titanium, tungsten, SS, cobalt, chrome, and nickel based super alloys are going to be used. As I told you, structural components for engineering applications in aerospace and custom made bio implants. So this is the most key role for making of the dental implants and custom made implants. And coming to the case of drawbacks, is extremely expensive when compared to other process, and vacuum generation is also takes much time. So just we are going to see the video of this, how this electron beam melting is going to be done. As you can see, this powder is going to be fed, and in the closed chamber and clean environment, this electron beam is going to be, the tungsten filament is going to emit the electrons, and complex contour melting is going to happen, evenly supplied. And you can see the electron beam, that's a bombardment of electron beam, and complex contour profile and contour melting also is going to happen. Powder heating and contour melting, you can see here. Hatch melting. So this beam control and fast accurate, and because this entire setup is going to equip with the several softwares, and temperature is going to exceed to melt the temperature is 1000 degrees centigrade, that and also depends upon the material. And high improved mechanical properties is going to be achieved with this electron beam melting. So this is how the part is going to be built, and then is going to be taken outside. Right. So this is the working of electron beam additive manufacturing. And multi-jet molding or polyjet. So most of the people will confuse the difference between binder jetting and polyjet. The other name for multi-jet molding is also called polyjet. So there the binder is going to be dispensed to cure the powder, and here photopolymer liquid is going to be dispensed by the nozzle, and it is going to be cured by the UV light. So this is the main difference between polyjet and metal jetting. And polyjet, the other name for this metal jetting is that metal jetting or polyjet, and that is called as binder jetting. So the difference between polyjet and binder jetting is mostly is that is going to dispense the binder. This is going to supply this powder, this entire photopolymer liquid is going to dispense the liquid on the surface of the build platform, and it's going to be cured by the UV light. So as soon as the first layer is going to be complete, the elevator platform moves downwards, and second layer is going to be dispensed on the previous layer, and it is simultaneously this head, this called as a printing head. So printing head is going to be have the dispenser nozzles and also with the UV light. So as soon as the dispensing is going to be done, the UV light is going to be used to cure the layer simultaneously. So this is a working of multi-jet molding or polyjet. So mostly it is going to be done by the 3D systems in 1996, and you can see this the stop multi-jet printing. And coming to the case of maximum build size, 1000 by 800 by 500, and resolution is 450 dpi and 16 microns, and cost is high. And key application areas: automotive, defense, and aerospace, and for medical applications. And coming to the case of drawbacks, accuracy is not that much good when you compare with SLA process. So just a small video of this metal jetting or polyjet. See, as soon as the print head is going to dispense the photopolymer liquid, and it is going to be cured by the UV light. So this is photopolymerization again. Here for same thing, the photopolymerization is going to take place as soon as the liquid is going to be exposed with the UV light. You can see the parts which is printed. See here, this is a setup. This is a build surface. So it is going to dispense the photopolymer liquid. So you can see the nozzles is going to dispense the liquid. So this is the main difference between binder jetting and polyjet. There the liquid binder is going to be jetted, and here the photopolymer liquid is going to be jetted and going to be cured by the UV light. So this is the main difference and a key difference. As soon as every layer is going to be deposited, the build platform is going to move downwards. This is so. After that, the part is going to be removed, and then additional post-processing is going to be done in the outside. So these are the different additive manufacturing processes which are discussed based upon the classification of liquid-based, powder-based, and solid-based. So thank you. Thanks a lot for seeing this valuable session. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.